One of the great joys of extending the internet to the world of real things is that they move around. And one of the things we want to know about all these real things is that they are, in fact, moving around. But at the same time, that's one of the great challenges. It's hard to do networking and get data from stuff that's moving around. And so that's exactly what we're going to talk about on today's Tech Talk here at IBM Developer Tech Talks. My guest today is a return presenter. His name is Kalanji Bankole, and he's based out of Los Angeles. He's one of our IoT experts, and his previous Tech Talk on long-range Wi-Fi was very well received. And we're going to talk about that more today, as I understand it. Isn't that right,
Yes.
Kalanji?
Exactly.
Sorry.
Right.
Where are you? So tell us a little bit about the motivation behind today's Tech Talk and how you got into this type of networking.
So essentially the motivation behind this one, so I can start with a bit of context. So the idea is this is primarily around like just asset tracking. So tracking mobile assets using a DIY hardware setup, as well as like open source software and IBM cloud services. So the main reason this came into play was essentially there's wildlife poaching is essentially at an all-time high. So basically a lot more rangers are essentially using this, are using technology to track poachers and catch them in the wild and basically catch them in the act. So
Awesome.
it's, yeah, basically.
So before we let you dive into that and help us catch the poachers, I just have to do just a little bit of housekeeping, which is to say that if you're watching us on the YouTube page, note that there's a chat window to the right of Kalanji's window. And if you have a question or a comment during the presentation, type your questions there. I'll be monitoring the chat, and I'll either ask your question immediately or hold it to the end so that we can kind of keep things flowing. Also, I want to note that in the description field, which is directly below the window, there is a link. The very first link in that description field is a link to the event page for today's Tech Talk. And that's important because you can get the replay for today's video at that page, as well as links to the code pattern in the GitHub repo so you can get the code for yourself, as well as other getting started resources. You can subscribe to our Developer Webcast Calendar there, as well as get yourself a free IBM Cloud Lite account. So do yourself a favor, either during or after today's presentation, visit that event page link. And once again, that is the first link in the description field below the video player. All right, with all that out of the way, help us catch some poachers, Kalanji.
Sure thing. So I'm going to share my screen. Okay, so as I said,
click that hide link button too.
Oh, sure thing.
Awesome.
Okay, so as I said before, so this is mainly around tracking mobile assets using a DIY hardware setup. So all these components are readily available online, and basically, so we're just going to be talking about focusing on an implementation that can be used to monitor endangered animals in the wild and essentially use analytics to detect if there are potentially poachers in the area. So just the overview of the problem statement. So researchers found that certain animals react differently to various disturbances. So whether that be a natural predator, a tourist, or a poacher. So for example, if a gazelle sees a lion, then they'll basically run away together in a certain formation. But if they detect a person that they feel threatened by, then they'll basically like scramble and zigzag out in multiple directions. So essentially by constantly tracking the movement pattern, the speed, the location, and so on, it's possible to essentially generate predictive analytics models to classify threat levels based off that animal movement. So basically an early warning system can be used to notify park rangers in advance and potentially catch poachers in the act. And one thing to point out is that we're not tracking the endangered animals directly because essentially if that information was intercepted by poachers, then that would be an issue. But so rather we're tracking other animals that are in the area. So like zebras, wildebeest, buffaloes, etc. So for the implementation, so to do this, we will at least need the following deliverables. So we will need a wireless network in which we can send sensor data over. We'll need some wearable sensors, and we will need servers to process and persist the data. And essentially, the server can also create predictive analytic models. And so this is basically just like what the high-level architecture would look like. So we would be delivering this data over the air using a protocol called LoRaWAN. So this is a relatively new wireless communications protocol, and it's ideal for IoT projects such as this one. And essentially, this is because we're able to enable sensors to send data at a long range, all while using a minimal battery usage. And one of the main drawbacks is the limited bandwidth, because you can't really send larger data formats like picture and audio. But in this situation, we'll mostly just be sending sensor data as small text packets. And so, for example, that would be like accelerometer data, location, temperature, etc. So bandwidth shouldn't be a concern. And before, sensor data for animal tracking would mostly be sent over cellular networks, but that could be quite expensive, and also cellular networks aren't available everywhere. And so, yeah, like I said, it would probably not be available in the area where the animals are traveling, but GPS likely it would be available. So going from left to right, we'll have some sensors learned by whatever animals we'd be monitoring. And these sensors are each wired to a LoRa-enabled microcontroller, so basically Arduino. And so generally, we refer to these LoRa-enabled sensors as a end node. So as the end node transmits wireless network packets, they're then picked up by the gateway as long as it's in range. And at the low end, gateway can have a range of a few kilometers, but higher end gateways can reach up to hundreds or even thousands of kilometers in some rare cases. And so from there, as data is received from the gateway, then it can then be uploaded to cloud services, and we can actually do something with that data, like create an app or generate models. All right, so starting with the hardware, the first step was to assemble a LoRaWAN Gateway. And so this is basically the central connection point for all incoming sensor data. So this should be in a secure location, and essentially somewhere that has both power and internet connectivity. So I was able to assemble a gateway by adding a LoRa concentrator module and an antenna to a Raspberry Pi. And I also had to install some software some open source software called LoRaWAN Server on it. So the end result is shown in this picture. And this is an example. This is just a drawn up schematic of a base end node. So I've used the Adafruit Feather MO, which needs a bit of additional wiring out of the box as shown here. So an implementation of the schematic shown here should be enough to send at least a hello world payload from the end node to a gateway. And so we can add components onto the end node, of course. So in this case, since we're focusing on asset tracking, then I opted to add a GPS module. So this is essentially this is a GPS module that's generally used for drones. It's a Neo 6M. And basically, I just had to do a bit of light soldering here. So I had to add the header pins, solder in the header pins into the 4 headers that we see at the bottom of the module. And this just basically like made it easy to insert into a breadboard. And also the antenna was able to screw right in at the top left corner here. So this is a picture of the finished result, which is kind of hard to follow, I'm sure. So I've also drawn up a simplified schematic here. So the GPS module has 4 pins, 2 serve as transmit and receive pins, and the other 2 are for power supply. So in the schematic here, the vertical wires are responsible for handling the positive and the negative voltage, and the horizontal wires carry the data. So this carries the data from the receive and transmit pins, as you see here.
Hey, Kalanji, quick question. And I apologize if I missed you saying it earlier. Just approximately, what's the retail cost for these components that you put together here?
So the feather is about, I believe it's about $25, and the GPS module should be about $7.
Okay,
Yes.
so this is easily a do-it-yourself weekend project then.
Yes, pretty much. Oh, but well, one thing, so this will require a gateway. So you can actually like set up these end nodes to talk to each other in a mesh network. But if you want like that longer range, then you might need a gateway. So essentially that Raspberry Pi along with the LoRa concentrator is about $150.
Okay, all right.
Yeah, but with a single gateway.
$30 per end node is not that bad.
Yeah, right. Yeah, exactly. Okay, so we've got our GPS module set up. So essentially this is just a example of the raw output that we would get from the GPS, a raw GPS payload. So this is a standard created by NMEA, essentially the National Marine Electronics Association. So since we're dealing with limited bandwidth, of course we only want to like send up a portion of the payload. So essentially I just want the longitude and the latitude. So to do this, I utilize a library I found on GitHub called Neo GPS, and I've pasted a sample snippet here. So basically the first few lines just import the library, and they initialize variables to query the GPS data. So after initialization, we can essentially load the last received GPS values into a fix, which is basically a struct. And then we can just reference fixed latitude and fixed longitude to basically parse the data. So you'll see those on lines 8 and 9. All right, so at this point, we should be able to view the location of any animals we're tracking, but we probably need a bit of additional data. So we also pulled an accelerometer, which has the ability to measure sudden movement and acceleration. So, and this particular accelerometer also has the ability to measure the orientation or the tilt of the wearer. So essentially you could tell like whether the animal's like laying down or standing up and moving, etc. So after designing a circuit, the hardware will need to be embedded into an enclosure of some sort. So this is an example of a set of collars that have been deployed on zebras in South Africa by Watson IoT team. So I believe it was designed and deployed by some students from a university in the Netherlands. I don't want to butcher their name, but I have it listed at the bottom. And also MVN, which I believe is a communications network out in Africa. Okay, so at this point, we are able to get data from a mobile sensor into a cloud. And we basically have our end node sending data to a gateway, and then the gateway forwarding everything to cloud services. So the next step would is essentially to build an application to make some sense of the data and basically just like visualize it. So here we have the architecture of a sample application that we've recently released as a reference. So the purpose of this application is basically just to like show all registered assets on a map. And basically this map is generated by the Leaflet and Esri libraries. So in this case, our end nodes publish LoRa packets from the end node to a gateway. And then basically the gateway forwards everything to the Watson IoT platform using the MQTT messaging protocol. And if you don't have MQTT installed, then HTTP works as well. And you could just like publish it. And and also the IoT platform uses the historian plugin, and this basically saves all location updates to a cloud database. And the UI, which is subscribed to a channel on the IoT platform, receives location updates from each asset in the field, and also draws a marker showing the real-time location of the asset. So these are just a few screenshots of the app functionality. So essentially, the user can fill out a form and input a node ID, location, and additional sensor metadata. So for example, we'll just use the decibels to measure sound in this case. So when the user submits a request to register a new asset and essentially show it in the map, then we'll call a method to draw a marker at the specified location using L marker, basically leaflet marker. And we can also create a list, so essentially just like an array to store all location updates. So we can just like persist that in memory, and as well as the time that they were received. And if additional metadata is received, like in this case, then we can draw a circle around the marker as well. So where the size corresponds to the center value. And these assets can be added to the UI through a form, but of course, most asset updates will need to be handled automatically. So they can also be submitted by publishing an MQTT message to the IoT platform. And essentially, this would need to forward a JSON payload that includes the same properties. So longitude, latitude, ID, center values, etc. And so here we have an example of an MQTT message being called from a CLI. So the first line contains the credentials and the rest contain that JSON payload. And this code snippet just shows the method of where the front end subscribes to the MQTT message bus. So you'll see that in the first the second line, we're just specifying like which channel we want to subscribe to. And then we have this MQTT client on message arrive section. And so like this is essentially a function that gets executed every time a new message comes into that channel. And so you'll see that as soon as like a new payload comes in, as long as the message is valid, then we'll just like call that init trackable asset method shown below, shown in the previous slides. And basically the submitted asset will show up on the leaflet map like so. And if sensor data is included, then it'll also create a circle, basically showing like the heat map of the node if any sensor data was included. And we can also import data from CSV files. So if you have data that's already been collected or generated, so you just have to like essentially specify exactly which columns correspond to location and time and etc. So here I have a public data set of water buffalo in Botswana. And so as you see here, I'm just specifying exactly like which columns I want to focus on, or which columns correspond to that location and time. And so this is the result after importing that CSV file. And also clicking show asset paths will essentially draw a line for each registered asset. So that basically just like shows their path or their previous locations. So this is done by essentially calling the draw asset path method. And so this essentially just like takes that, it basically takes that array of various longitude, latitude points that we generated earlier, and it creates what's called a leaflet polyline. And then once that polyline is generated, then it's added to the map on this last line here. So at the moment, I think that's pretty much it I have for now. So I wanted to see if there were any questions. And also I've included references as well. So the first reference is just the link to the GitHub repository. And I also have a slide share where I got the pictures of the collar fitting as well. And there's also an article from the university responsible for the project.
All right, that's terrific. Thank you, Kalanji. We don't have any questions right now, but I wanted you to go back to the part where you were talking about how something about how they could analyze the patterns of the animals in different situations and infer what's in the area. Could you talk us through that again?
Yeah. So essentially, you would have to generate a machine learning model. So I haven't got too far with that as of yet, because essentially you also need you do need like input. I mean, you can use simulation data, but you need input data of the animal movements.
Oh, okay.
So I was able to find like data of the animal movements, but I also need data of when these poaching events occurred. So like where they occurred and like what time as well. So this is so essentially the previous project was something that was like kind of like used live and like monitored by rangers in real time. And so like basically that's how like they were able to train their models.
Got it. And what's really interesting to me, I like the fact that this project can get the real-time data from the devices, but it can also import historical data via CSV files or whatnot, so that you can in fact get a large enough historical data to do some model training. So I think that's really interesting.
Oh yeah, definitely.
All right, I think that's it. We don't have any questions. We do have a couple of people on the chat saying thank you for a good presentation. So thank you, Kalanji, for your time today. And with that, folks, we will wrap it up. I will put it's not up there now, but I will put up Kalanji's presentation on the event page just as soon as I can. So once again, the event page is that first link in the description field. The event page has the replay, links to the code, links to the pattern page, everything you need to get started with this. One last question, just for clarification. Everything we saw today, can you do that with an IBM Cloud Lite account?
Yes, you can.
Okay. So we give you everything you need to play around with the code yourself on an absolutely free IBM Cloud Lite account. So go get yourself an account, get the code, play around with it for yourself. With that, I'll say thank you, Kalanji, one last time.
Cool. Thank you.